The concept of spacetime, intertwining the three spatial dimensions with the temporal dimension, stands as one of the most profound and revolutionary ideas in modern physics. Its development is a tapestry woven from centuries of philosophical inquiry, mathematical innovation, and empirical observation. This narrative traces the evolution of our understanding of spacetime, from the philosophical musings of ancient civilizations to the sophisticated theories of contemporary physics. Antiquity and classical views. Ancient philosophical roots. The early Greek philosophers were among the first to grapple with the nature of space and time. Plato, in his work Timaeus, introduced the idea of a receptacle space, an abstract domain where the physical universe resides. However, he did not connect time with this receptacle. Aristotle, in physics, provided a more systematic analysis. He defined space, or place, as the boundary surrounding a body, essentially a container, and time as a measure of change. To Aristotle, space and time were distinct and separate entities, not interwoven as they are in modern conceptions. The Hellenistic and Roman contributions. Following the classical period, Hellenistic philosophers, such as the Stoics, offered alternative views. The Stoics conceptualized an infinite void, a precursor to the modern idea of an infinite universe. However, they too maintained a distinction between space and time. In the Roman era, thinkers like Lucretius in De Rerum Natura echoed these views, emphasizing a universe filled with atoms moving through an infinite void, with time as a continuous, separate backdrop. The Middle Ages and the Renaissance. Medieval scholasticism. During the Middle Ages, the synthesis of Greek philosophy with Christian theology led to new perspectives on space and time. Medieval scholars, influenced by Aristotle and the Neoplatonists, debated the nature of the cosmos. Thomas Aquinas, for instance, adhered to the Aristotelian view of a geocentric universe with a finite space and a linear unidirectional time ordained by God. The Copernican Revolution. The Renaissance marked a pivotal shift with the Copernican Revolution. But Nicholas Copernicus, in his De Revolutionibus Orbium Coelestium, 1543, proposed a heliocentric model, challenging the Aristotelian geocentric universe. This paradigm shift, while primarily astronomical, set the stage for a reevaluation of space and time. The birth of classical physics. Galileo and the nature of motion. Galileo Galilei's work in the late 16th and early 17th centuries further revolutionized the understanding of motion and time. His experiments with falling bodies and inclined planes established that the laws of physics are the same for all observers in uniform motion, a principle that would later underpin the theory of relativity. Newtonian mechanics. Isaac Newton's Philosophiae Naturalis Principia Mathematica, 1687, formalized the concepts of absolute space and absolute time. Newton postulated that space is an infinite, unchanging stage where the drama of the universe unfolds, and time flows uniformly and independently of the material world. His laws of motion and universal gravitation provided a comprehensive framework that dominated physics for over 2 centuries. The advent of relativity. The prelude to relativity. By the 19th century, inconsistencies in Newtonian mechanics began to emerge. The study of electromagnetism, particularly James Clerk Maxwell's equations, suggested that light speed is constant, contradicting the notion of absolute space and time. Special relativity. In 1905, Albert Einstein published his theory of special relativity in the paper on the electrodynamics of moving bodies. Einstein proposed that the laws of physics, including the speed of light, are the same for all inertial observers. This led to the revolutionary idea that space and time are not separate entities, but are intertwined in a 4-dimensional spacetime continuum. Key consequences of special relativity include time dilation and length contraction, where time slows down and lengths contract for objects moving close to the speed of light relative to an observer. General relativity. In 1915, Einstein extended these ideas to include gravity with his theory of general relativity. He proposed that massive objects cause space-time to curve, and this curvature affects the motion of objects, which we perceive as gravity. General relativity fundamentally altered our understanding of gravity, space, and time, providing new predictions such as the bending of light around massive objects and the time dilation experienced near strong gravitational fields. Spacetime in the quantum realm. Early quantum theory. While general relativity describes the macroscopic universe, the early 20th century also saw the rise of quantum mechanics, which governs the microscopic world. Quantum theory introduced concepts that challenge classical intuition, such as wave-particle duality and the uncertainty principle. Quantum field theory. The development of quantum field theory, QFT, in the mid-20th century aimed to reconcile quantum mechanics with special relativity. QFT describes particles as excitations in underlying fields that permeate spacetime. However, integrating QFT with general relativity remains an ongoing challenge, as the two theories are fundamentally incompatible at the Planck scale, where quantum gravitational effects become significant. Contemporary theories and speculations. String theory and M-theory. One of the most ambitious attempts to unify quantum mechanics and general relativity is string theory. Proposed in the late 20th century, string theory posits that the fundamental constituents of the universe are not point particles, but one-dimensional strings, whose vibrations determine particle properties. String theory naturally incorporates extra dimensions beyond the familiar four of spacetime, suggesting a richer and more complex structure to the universe. M-theory, an extension of string theory, proposes that these strings are actually one-dimensional slices of higher-dimensional objects called branes. M-theory aims to unify all consistent string theories and suggests that our universe may be a three-dimensional brane within a higher-dimensional space. Loop quantum gravity. Loop quantum gravity, LQG, is another approach to quantum gravity that seeks to quantize spacetime itself. LQG suggests that spacetime has a discrete structure at the smallest scales, composed of tiny loops or spin networks. This theory provides a framework for understanding how spacetime geometry could emerge from quantum processes. The holographic principle. The holographic principle, inspired by black hole thermodynamics and string theory, posits that the information contained within a volume of space can be described by the information on the boundary of that space. This idea challenges conventional notions of dimensionality and has profound implications for the nature of spacetime and gravity. Experimental probes and observations. Modern technology and astronomical observations continue to test and refine our understanding of spacetime. Experiments such as the detection of gravitational waves by LIGO and Virgo and observations of black hole shadows by the Event Horizon Telescope provide empirical data that challenge and confirm theoretical predictions. Cosmological implications. Theories of spacetime also play a crucial role in cosmology. The Big Bang theory, supported by the discovery of cosmic microwave background radiation and the observed expansion of the universe, suggests that spacetime itself has a dynamic history. Dark energy and dark matter, which influence the large-scale structure and fate of the universe, further complicate the picture of spacetime. Philosophical and conceptual reflections. The nature of reality. The evolving understanding of spacetime raises profound philosophical questions about the nature of reality. Is spacetime a fundamental aspect of the universe, or is it an emergent phenomenon from more basic principles? The interplay between mathematical elegance and empirical validation continues to shape these debates. The role of mathematics. Mathematics plays a crucial role in describing and understanding spacetime. The abstract nature of mathematical theories often leads the way in predicting new physical phenomena, as evidenced by the success of general relativity and quantum field theory. The search for a unified theory of spacetime continues to drive mathematical innovation. Human perception and spacetime. Human perception of space and time, rooted in our evolutionary history, often conflicts with the counterintuitive nature of modern physics. Bridging the gap between intuitive understanding and theoretical concepts remains a challenge for educators and communicators of science. Conclusion: the history of spacetime is a testament to the power of human curiosity and intellectual progress. From the philosophical musings of ancient civilizations to the cutting-edge theories of contemporary physics, our understanding of spacetime has evolved dramatically. Each new insight builds upon the work of previous generations, leading to a deeper and more nuanced appreciation of the universe's underlying structure. Thank you for watching. Please subscribe our channel.